Okay, uh, greetings everyone. Welcome in to my channel. Um, Happy Wednesday. I hope everyone's doing well. And yeah, I am Professor L, and I am having a live stream for math tutoring. So if you're out there and you feel like hanging out and doing some math, you're welcome to post a math problem in the chat and I will do my best to work it out. In the meantime, I have picked out a system of nonlinear equations that I am going to attempt to solve algebraically, and in the meantime, sketch the graph. So yeah, and do my best to explain about these two functions that I picked out. So I'm going to go ahead and just get into it. Systems of equations, recall, when you have a system of equations, if you have a solution, what you're looking at is clean intersections of where these functions are touching in their graphs on the Cartesian coordinate system. So we're talking about specific locations in the graph that have the same x and y components. And with systems, you can have multiple variables, but what you have to have in order to solve a system is for each variable that you introduce into your system, you have to have a separate and unique equation for each variable. So if you have two variables, you need two separate unique equations in order to solve the system. And if you had three variables, you would need three separate unique equations in order to solve your system. So that's kind of like a mini nutshell theory behind solving systems of equations and multivariable. When you get into multivariable, you're looking at probably using matrices to solve your systems, but 2 and 3 variable are pretty easy to handle mathematically, and so those are the ones that I like to play around with because yeah, I like I guess the more easy math, I guess. It's kind of something that you'd hate to admit. Okay. That you prefer things easy, but I'll go ahead and I'll admit that. All right, I prefer pretty easy functions, but it doesn't always work out that way. All right, so here we go. Graphing a non-linear system of equations. And I wish I knew more about my camera. I need to figure out if there's a way to get it to focus a little bit better, because I noticed that today the camera didn't seem like it was focusing. Okay, so, but I'll just make do the best I can with what I have. All right, so this system I have picked out, this is a circle. So we have, oh, wait, that's not right. It's x squared plus y squared equal 25. And then it's a hyperbola, so it's x squared minus y squared equals 7. And I just picked this one out today, and I started looking back on what I knew about hyperbolas. And because we've kind of already talked a little bit about circles, and I put the standard form of the equation on a circle, or for a circle up here a couple times. Tonight I thought I would play around with the standard form for hyperbola. And I'm not going to claim to be an expert. I just would like to kind of revisit and get more familiar with a concept that I years ago was somewhat familiar with. So hyperbolas, I had to actually pull up the general equation for them. And so I kind of want to put it up here. And where does this? It's x minus h, oops, quantity squared. And I don't have this memorized, so I'm just reading it off of my screen, over a squared minus y minus k quantity squared over b squared equal 1. And let's see, what are the two differences between those two? Oh, they switch them. So you can either have the x term listed first, or it would be like this, the y term. So y minus k quantity squared. So whatever term is positive, in order for it to be a hyperbola, one of these terms is going to be negative. And so what's going to happen is you're going to list in standard form. We'll put standard form up there. And standard form, even for lines, it's kind of picky. It wants a positive number listed first. So that's the only difference. So it would be b squared minus x minus h y squared over a squared. Just so basically what you're doing is you're associating the values k and b squared with your y component and h and a squared with your x component, your first component and your second component when you're graphing your ordered pair. Anyway, yeah. So hyperbolas, basically, I'll just sketch a basic graph of a hyperbola. What's happening is it has two intersecting diagonal lines that make its up its asymptotes. It's a really funky graph. And what happens is it has a focus. Let's see, it comes up like this, and it bends towards those asymptotes and creates this symmetrical graph that it's almost like a parabola, only there's two parts to it. And it's about the x-axis. Parabolas can have, I guess they can have y-axis or x-axis symmetry. Hyperbolas, basically, the graph, it's creating this thing where it exists in two different parts, essentially. And so a hyperbola is kind of related to a circle in the respect that it is a conic section. And so conic sections, let me see if I can list them all. So you have the hyperbola, the parabola, the ellipse, ellipses, and the circle. I don't think I'm leaving any out. And basic and we'll probably have to talk about this later if we graph ellipses, or any other conic sections. But basically, how you determine whether it's a conic section or not is the eccentricity. And eccentricity is a number, it's a ratio. And what it does is it describes how it's a ratio of deviation from a circle being perfect. So if you think about the roundness of a circle, where it has a perfect its perfect shape in regards to it has a center and the radius, no matter where you put that radius on the circle, it's always going to be the same distance. But if you have like an ellipse, if you have an ellipses, you've got something that's not, it's got symmetry, but it's not got a perfect. So if you try to take a radius from here and here, obviously you've got two different distances. And it's the same thing with the hyperbola. Well, they have, all of the conic sections have this eccentricity value. And basically how you determine whether, just verifying looking at the graph, how do you tell whether it's a circle, a hyperbola, or an ellipse? Because those graphs look so close together, similar, that you would go and you would find the eccentricity, and then you would also put it in standard form. And then you'd be able to determine by looking at the graph what kind of function it is, or what particular conic section you're dealing with. But instead of having a center, what it has is it has these asymptotes, and it has these other values. They're called a focus and a directrix. And so if you have your equation in standard form, let me see what it says. It says, yeah, the difference between the 2 points on the x-axis would be your focus. And you find them by this value. It's a comma 0. Let's see, because you have a value on the x-axis and y is 0. And it's going to be negative a comma 0. And then you find it by taking a squared equals, okay, this one I'm not sure. It's a squared yeah, so you're solving a squared equals x, I guess, essentially. That's what I was thinking, but not sure. Anyway, so this would be how you find your focus. And then there's also a way to find the directrix. The directrix is another value that we would probably need to graph the hyperbola. Anyway, I think that we're going to be able to just take this value here, and because this is my circle, so this is a circle, and this one is the hyperbola. And the reason why I know that is because of this plus right here. That's the only thing that's making that equation. this negative right here is making this equation do funny things. But I think that we'll be able to graph it. And yeah, we're just going to try to do it. So that's basically, I think the directrix is the H comma K. But I guess I could look that up real quick. Let me see. Anything else I want to, I don't want to spend a whole lot of time trying to figure out all of these values of the hyperbola. I want to get back to the system, but I guess I need to figure it out. And no time like the present to try to remember about these details. Okay, so the directrices of a hyperbola are two vertical or horizontal lines that define the shape of the curve in conjunction with the foci. The lines are perpendicular to the transverse axis centered at a distance a over e from the center. All right, so it's probably going to take me a little bit longer to remember all that stuff because that was a really lengthy, they just said a lot of different definitions in there. And so I'm going to have to go back and study and think about the hyperbola a little bit longer. But that's the vertex. Okay. The focus is here. And they're called foci. Yeah. This is the vertex, so I don't want to tell you wrong. That's the vertex. These are the foci. All right. And this is exactly the reason why I picked the hyperbola. I picked this one because I was like, I just want to play around with it. And they are kind of funky graphs and they are kind of complicated. They're the different ones. They're the conic sections that I felt like were the hardest ones to graph. But we're going to give it a go. Anyway, let's go ahead and sketch our Cartesian coordinate system. And just see how this goes. And again, you can graph your system, solve it graphically, but you can also solve your system by algebra as well. So if there's a lot of, so the vertex here would still be at h comma k. Okay. And so it has a lot of similarities to the circle. So we'll just know that. And I'm going to erase all of this because I was just trying to kind of give a very, very brief introduction to hyperbolas. And I say brief in every sense of the word because I don't know a whole lot about them right now. I'm going to try to go back and relearn a little bit more about them because you have the hyperbolic functions that you learn about in calculus. So I know that the hyperbola is very important in upper level math, but at this point in time, I limited knowledge. All right, but what I can do is I can use that the center of the circle, and I can say x squared over a squared minus y squared over b squared equal 7. And then what we have to do is we have to make this number 1. So we're going to, basically it's going to be we're going to divide everything by 7. So you're going to get oh, x. What did I do? A squared, b squared. And then what we're going to do is we're going to put x squared minus y squared equal 7 divided by 7. And then you're going to have x squared over 7 minus y squared over 7 equal 1. And then a squared equals 7 and b squared equals 7. And then taking the square root of a, I'm going to get plus or minus 7. And that is going to tell me my, I think that value a comma 0 and negative a comma 0 is the one that I calculated. So then you would have, you have two values. So you have negative radical 7 comma 0 and radical 7 comma 0. All right, so we have these two critical values on the graph of that hyperbola. Let's see, and what else do I know how to find? All right, so let's go ahead and graph those two values. And because I know for a fact that I know how to solve for that one because I looked at one up earlier. And I probably should have graphed it earlier, but that's okay. So I have to get my calculator out and figure out what radical 7 is. Square roots. But I need my table. So I'm going to put the table over here. Kind of like the table over here. I can leave enough room ahead of time. X, Y. And we have so this is saying 2.64. We'll go out to -3, I guess. Or -4. We might need to go out to -4 on this one. -3, -2, -1, 0, 1, 2, 3, 4, just to get a nice symmetrical graph. And then radical 7 is lying in here in between. And so there's a negative radical 7, so I need to go ahead and skip that down. So instead of the -2, I guess, we can do the negative radical 7 and then +2. We'll put a positive radical 7. See if that works out. Because I know those points are my zeros. Yeah, hyperbolas. Just know that there's some funky graphs out there, and I'll probably want to research hyperbolas again because I'm starting to remember. And part of this is me realizing how much I've forgotten. So it's okay. We'll just roll with it. All right, so I'm going to go ahead and graph those two values. we're going out to -4. So it's 1, 2, 3, 4. And instead of -2, we're doing negative radical 7 here. And it's about, we'll put it on here. Radical 7 is 2.6457 51311. And we've got positive radical 7 in here. And it's it's just not going to be exact. We'll say we'll do it legitimate. This is negative radical 7 because that's -2, -3, -1, -4. That looks a little bit better. And hopefully, -1. Oh, I need to calm down. I'm putting negatives over here in positive land. I need to just take a deep breath. All right. Because I want to make sure I'm practicing the right thing. I want to get good at being bad. All right. So we got 4. And then, so we've got positive radical 7 in here. Okay. And I'm going to go ahead and draw my intersections. And wish that I knew some other values in this function. So what I was thinking was if there was another way, so I've got the function rearranged here, and I need to be able to solve this function somehow really easily to plug in values. So I was wondering how I could do that. And so let's just see. I'm going to go ahead and erase all of this stuff because I might need the room. We'll just see what happens. And I do want to solve it algebraically, but I was trying to pick one that was going to be a little bit harder, and I guess I did a good job on that. All right, so we got x squared minus y squared equals 7. And what's going to happen if I solve this one for y? And I'm just warning you, I don't know what's going to happen here. If this is going to be fruitful or not, but I'm going to try and solve this for y. So subtract x squared from both sides. And you're going to get negative y squared equal 7 minus x squared. And then I'll multiply everything by a negative. Go y positive. So that's going to be y squared equals, was that negative 7 plus x squared? And then that's going to lead to, so we'll just switch orders with those terms. So that's y squared equals x squared minus 7. And then take the square root of both sides. You're going to get y equals plus or minus the square root of x squared minus 7. And that's going to lead to 2 graphs. So you're going to have a positive and a negative. So that's going to lead to symmetrical values. And so we're going to plug these points in, but just know that, well, first of all, if it goes negative, you're going to end up with points that are not going to appear on the graph because they're in the complex plane. And that's like a whole nother like can of math worms that, you want to the complex plane. So right now we're just dealing with Cartesian coordinate system with rectangular coordinates, they're called. But there are other planes that and coordinate systems out there, just so you know. And so that's, if you end up with negatives, then you're going to end up with issues that also you can't divide by negative. So, all right, let's see what we're doing. Our vertex is at the origin for our hyperbola, I believe. All right, anyway, so we have this function here, and I call it a function. It's I guess I'm not sure if it would pass the actual function test because I haven't looked at the domain of it yet, but we can go ahead and evaluate this function at those values. So that's really what I want to do. So let's go ahead and start by plugging in when x equals -4. So x equals -4 in this function, see what happens. So you get y equals, and we'll just take the positive one for now, the square root of -4 squared minus 7. And I like that because it's probably not going to go negative because of that square, but you never know, because if it's a 1, then it's going to go negative. All right, so we've got the square root of 16 minus 7. And that's going to work out nicely because that is the square root of 9. So that is 3. So at -4, I have plus or minus 3, I think. That's what that means. So at 4, I have a value 1, 2, 3, 4. I have a value at 3 because it's a plus or minus. Okay. 1, 2, 3, 4. -1, -2. Yeah. So we have +3 and -3 on the ground. And then we plug in. So we have two values. We have +3. So I'm just going to put it on there plus or -3. Okay. Plus or -3. All right. And then for -3, let's see what works out. So x equal -3. Y equals plus or minus the square root of -3 squared minus 7. So that is going to be 9 minus 7. The square root, or the square of a negative is a positive. So that is going to be plus or minus radical 2, it looks like. 9 minus 7 is 2. So at -3, we've got plus or minus radical 2. And radical 2 is 1 point something. 1.4142. $13562. Okay. Okay. So we've got at -3, we've got plus or minus 1.41. So it's like right in there. And here. So this is actually giving me a pretty good idea of my parabola here. And what's happening is you have a symmetrical graph over here. So we've got radical 7, radical 2 is, I want to see what happens when you plug in radical 2, but the graph disappears and it doesn't reappear until you get over here to radical 7. So, but I am curious what happens. So I put them on here. Let's just plug in and see what happens. So x equal, let's do, since we don't have -2 on there, we have -1. Or if it's going to be a 0 or it's going to be a complex solution. All right. So we've got y equals plus or minus the square root of -1 squared minus 7. So this is -1 squared. That's 1 minus 7. Plus or minus the square root of -6. That's plus or minus the square root of 6i. So you've got these values. Plus or minus the square root of 6i. And then also for 0, 0 is going to be plus or minus radical 7i. And then positive 1 is also going to be plus or minus radical 6i. And the reason why is because the symmetry of this graph, that square function, that x squared, this is y equals x squared. And because of this function right here is leading to symmetry. So we have 3 is the same as -3 here. It's going to be plus or minus radical 2. And then 4 is going to be plus or minus 3. So hang on, 1 is going to be complex solution. And then the graph starts at radical 7. And then at 3, we're at radical 2, which is between 1 and 2 here, and between 1 and 2 here. We're talking rough sketch. And then at 4, we're at plus or minus 3. Here and here. So we've got this sort of thing going on. Here's your hyperbola. I totally missed this one. Look, let's see if I can just fix it real quick. All right. So we've got that kind of thing going on. And that graph just does not look symmetrical at all, but that's okay. It's close enough. 1, 2. Okay. So let's see what I want to do next. All right. So what I want to do next is go ahead and sketch this circle. And that was pretty rough on the hyperbolas. I'm going to have to go and learn a lot more about that. It's good to know what you need to know. And sometimes you don't always know that. So it's nice when you realize it. Okay, so we have the circle and we have the theory behind the circle. So I don't really want to put that equation up again, but we have the center is at 0, 0, and the radius is at, let's see, well, r squared equals 25. So r is going to be plus or minus 5. So we need the square root of 25, which is plus or minus 5. So we've got r equal to 5. So for my circle, I have this point on here. And I'm just going to go out 5 in every direction. Hopefully my scale is a little bit better than last time I drew a circle up here. That was pretty embarrassing, but oh well. So I'll have this kind of thing going on. And I want to go ahead and find some more points in here. So I don't know where the points are in common. Feel like I need to have like an in-between point in here. So I'm kind of curious about, I don't know if 4 is on the circle or not. What I could do is I could start plugging in some of these points into the circle. So let's see, we got x squared plus y squared equal 25. And if I wanted to plug this into my graphing calculator and I didn't know anything about circular coordinates, then what I could do is I could solve this for y and I can just graph it regularly in parts. So if I did that, you're going to end up with a plus or minus radical, just like the previous hyperbola, and then you would just have to enter that in twice into your graphic calculator, and it would produce a pretty graph of your circle. So that's similarly what I'm going to do. I'm going to go ahead and solve for y by subtracting x squared from both sides. And just plug it in a couple points here. So we've got y squared equals 25 minus x squared. And then we're going to take the square root of both sides. And that'll give me plus and minus square root of 25 minus x squared. So if I want to figure out what is going on when x equal -4 on my circle, then I'll just plug in -4 and we'll do the positive and then we'll just negate it and then that'll be a twofer. So y equals the square root of 25 minus a -4 squared. So this is 25 minus -4 squared is 16. And is that 9 again? Square root of 9? 25 minus 16. So you're getting plus or minus 3. Nice. So for my circle, we need another table here. So x comma y. And we're going out, it looks like to -5 because that's my radius. So -5 is a 0. -4, I have plus or minus um, 3. -4, I've got plus or minus 3 on my circle as well. Nice. So that circle, what it means is it's also going to intersect at plus or minus 3 here as well. And that happens to coincidentally be my intersection. This is going to be my solution. So we've got -4, comma -3 here. We've got -4, comma +3. And then over here we'll have +4, 3, and we'll have down here, we'll have 4, comma -3 for our solutions. Good. That was luck. A little bit of luck. Okay. And again, completely butchered the circle. It has the eccentricity of 0, even though it looks like it's an ellipse. It's not. I think I need a little bit more practice drawing my circles, okay? But that's all right. I found that pretty quick. I don't really care about any other values on my circle. If we wanted to, we could go ahead and list these critical values, because what I've done is I've found my solution. So I'll go ahead and not give up. All right, so we'll go ahead and plug in when x is 0. And we've got, when x is 0, we got plus or minus 5. And then we don't have another point on my circle until I get to 4. And that's plus or minus 3. And then we have 5, comma 0 on there. So there's my table for my my circle. And all right. Almost an hour in. Let me see if I can solve this algebraically really quick so we can be finished. I was not planning on talking about math for another whole hour tonight. I was trying to split it up and make it like maybe 30 minutes, especially if I'm not working with students. But I just, it's getting a little bit easier to talk about the math. When I first started this project, it was a little bit harder for me. Okay, so we'll leave that graph up there. We go back to our equation, and we're going to remember our methods. So what we're going to do is we're going to eliminate y here by adding these two equations together. So if I add these equations together, x squared plus x squared is 2x squared plus y squared and minus y squared is going to go to 0. And then I got 25 plus 7. So that is going to be, was that 32? So I've got to divide both sides by 2. And x squared equals, is that 16? So you've got, you take the square root to solve for x, you're going to get x equals plus or minus 4. Okay. So it's telling you where the party's at, -4 and +4, which this is true. So then you're going to take either one of these equations to get your y's now. Okay. So I prefer positive. So I try to stay positive, but we're going to have to deal with negatives anyway. So we could just take that first one. Either way, you're going to go ahead and plug in. So you're going to say x squared plus y squared equal 25. And then we're gonna go ahead and solve for y again, like we did before. And that gave you y equals plus or minus that square root of 25 minus x squared. And then what we're going to do is we're going to use that, and we're going to plug in to, when x is positive 4 and negative 4, and we're going to get two values. So we're going to find out, so when x, so we'll go ahead and set out our order pairs, because this solution to systems of equations are ordered pairs that appear on the graph in the Cartesian coordinate system. So we've got 4, 4, negative 4, and negative 4. Because when you plug in 4 here, you're going to get two answers. When you plug in negative 4 here, you're going to get two answers. So that's going to lead to 4 different values, which we've already verified that graphically. We're just showing an alternate method. I like to solve them both ways. So we'll go ahead and take the positive, and then we'll just duplicate the negative. So that is radical 25 minus 4 squared. And that's going to give you 25 minus 16. We just did that, which is square root of 9, which is 3. So it's going to be plus or minus 3. So you have 3 and you have negative 3. And then when you plug in negative 4, when you square a negative, you're going to get the same answer. So that's going to be a positive 3 and a negative 3. And then there's your solution right here. Okay. All right, so we'll go ahead and call that good. Right in between, trying to stay in between 6 and 7. If I do get students, I don't mind going over on time, but it's a busy, hectic world that we live in, and so I need to be a good steward of my time and go ahead and not be too out of balance. Yeah, so I'll go ahead and call that good. And even though that was a little rough, we did successfully sketch the graph, and we found these solutions. And yeah, just for fun for me. And hopefully somebody will watch my video and maybe it will help them a little bit in some way. And again, I just want to say thank you for watching my video. And I will see you next time. Again, I'm Professor L, and I'm here Monday through Friday from 6 p.m. to 7 p.m. Central Time. And I look forward to being back tomorrow. Bye.